Okay, so we're going to do the recording here. Okay, section 2.1, the tangent and velocity problems. Okay, so, all right. Let me make the pen visible here. So, tangent is a big thing in calculus, right? Finding slopes of tangent lines to curves is very important. So a tangent to a curve is a tangent line to a curve, which you see right here. Well, actually, let's focus on this figure 1 here, this second graph. What you see is a function. And they've drawn a tangent line to the curve. Hold on here. I don't know why it won't draw it. I want to, hold on, let me just. There we go. Okay, there's a tangent line. And at this point P, right there, at that point P, we have drawn a line that's tangent to the curve. We've drawn a tangent line to this curve C at point P. Now this is central to calculus, finding tangent lines to points on curves. This is central to calculus. And in the first example, they ask, okay, let's find the equation of the tangent line to the parabola y equals x squared at the point 1, 1. Okay, so what they do is they draw the parabola y equals x squared. They use the parabola because that's something that you've seen many times, the y equals x squared. And the point 1, 1 is on the parabola. And they want to find, and they have a tangent line, okay, passing through point P, touching the curve. Okay, and just ignore the phone there. There's it's a landline. There's kind of nothing I can do about it. All right. So how are we going to find this tangent line? Well, what's important to find? And for any line to get its equation, what do we need to find to get the equation of a line? That's right, Ian, the slope. We have to find the slope. Okay. Well, you know, we have here, we have a picture here in figure 1 of y equals x squared, and we have the tangent line. So intuitively, geometrically, we see it there. So it must exist. The slope of that line must exist. So how might we find the slope of that tangent line? Well, what we can do is we can find the slope of something called a secant line. Okay, so the idea, you see, to get the slope of a line, how many points do you need? How many points do you need? You need, well, 4 coordinates, but you need 2 points. 2 points, an x1, y1, and an x2, y2. So what they say is why don't we pick, like, I want to show this the right way here. All right, let me just see if maybe I can, that's right, maybe. All right, I'm going to try to do something here on the picture so that it makes, I want to make sure I'm very clear. All right. Ah, that's not right. Hold on. So I'm looking at figure 1 here. I'm looking at figure 1. And I don't know why it won't. There, that's good. Okay, that's the tangent line. See that little T there? That's your tangent line. But the tangent line only touches the function at one point. So we only know one point on the tangent line, and that's the point 1, 1. To get the slope of the tangent line, we need 2 points on the line. Okay, we know that 1, 1's on the tangent line, but we don't have another point. So what they say is, let's try this. Let's draw, I want to say this the right way. Let's pick 2 points on the curve. This point here, 1, 1, and this other point right here. Okay, so I have here delineated 2 points, 2 big blue points, and both of these points are on the, they're on the function. Okay, so this second point here, all right, what's its coordinate? Well, they're saying the coordinate for the second point is, they're letting x be 1.5. Let me just see here. Let me make sure this thing's off. They're letting x be 1.5. And so this point here has coordinates 1.5, and then that's x. But then if you square 1.5, because y equals x squared, you're going to get 2.25. And I'll have to, I think everything's clear. It's a little bit thick, the drawing, but the writing, but it's okay. So do we agree that 1, 1, the coordinate 1, 1 is on the curve y equals x squared, and the coordinate 1.5, 2.25 is on the curve y equals x squared? All right, so we're agreed with that. Now, great, thank you. So what are they doing here? Well, you notice they have here a second line. They have here a second line. Okay. and this second line passes through those 2 points. But since the second line passes through those 2 points, we can find its slope. The yellow line, thank you everybody, the yellow line is the secant line. The red line is the tangent line. And what we're trying to do is approximate the slope of the tangent line with the slope of the secant line. So the slope of the secant line, okay, that slope of the secant line, which is the slope PQ, and you see there's P right there. There's P, there's the Q point, the other point Q. The slope is going to be the difference of the Y values, okay, which is 2.25 minus 1, over the difference of the X values, which is 1.5 minus 1, and that's 2.5. Okay, so that's the slope of the one secant line. But what we can do, you see, well, do you agree that the slope of 2.5 is an approximation of the slope of our red tangent line? Are you comfortable with that? All right, and great, and now that's basically what we know how to do, because, you know, we've learned that we need 2 points to determine the slope of a line. Okay, and you do, and that's what we have. But what they have here in this table, here, is they've picked some other X values. Okay, they've picked some other X values, 2, 1.5, 1.1, 1.01, and 1.001. So what they're doing is they're picking X values. They're picking X values here that are closer and closer to 1. Because remember, we want to find the tangent line to the parabola at the point 1, 1. So we're always going to use 1, 1 as one of the points. But we can also then, well, I want to say this the right way. So, you know, for your slope, you have a rise over a run. The one point you're always going to have is 1, 1, right? Because that point 1, 1 is it's always one of the 2 points you use. But like, for instance, if you decide that you want to let X be 2, okay, if X is 2, what's Y going to be? Well, Y equals X squared, so you're going to have 2 squared minus 1, that's 2 squared is 4. So 4 minus 1, or I should say 4 minus 1 is 3. That gets you 3 over 1, and that's how you get a slope of 3. You see that? Are we okay with that? Okay, thank you, Lynn. Excellent. Thank you, Sebastian. And what they're doing is they're saying, well, and thank you, Sydney, thank you, Shlo, or Kuklo, right? Tanya, and thank you. So what they're doing is they're saying, to approximate the slope of this red tangent line, let's use a slope of a secant line to approximate the slope of the tangent line. But the secant line, what they're doing is they're changing the X values so that the secant line gets very close to the tangent line. So if you let x be 1.001, your secant line is going to have 2 points that are very close to each other. The one point being 1, 1, the other point being 1.001, comma 2.001. So what's happening is they're computing slopes of 5 different secant lines, and as the x value, as they change that x value so that it's closer to 1, the slope is getting close to 2. And so this means that the limit as q approaches p of the slope of the secant line, that's going to approach 2. And that's what they're doing here. So Ian says it just tries to make the 2 points. Ian says they just try to make the 2 points as close as possible to the 1 point, and then use that to state the slope of the tangent. That's exactly right. That's exactly right. That's what they're doing in this table. And then in the second table, what they do, you see what they're doing is they're approaching the x equals 1 from the right by, 2, 1.5, 1.1, 1.01, 1.001. You're approaching 1, x equals 1 from the right. But you could also approach x equals 1 from the left. And that's what they do in this second table here. They're approaching x equals 1 from the left and computing the slopes of the secant lines. They compute 5 slopes. And the slopes of the secant lines are also approaching 2. So this leads us to believe that the slope is indeed 2 of the tangent line. And therefore, you can get the equation of the slope of the tangent line using the point slope formula. Okay, and this is sort of their way of finding the slope of that tangent line in the figure. Okay. And what they show here on the next page is they show, in this figure 3, they show the process that occurs in the example. So what they do here is the point P is always 1, 1. But they're taking the point Q and passing a secant line through P and Q. But they're letting Q get closer to P. They're letting Q get closer to P, the point Q get closer to P. And so what happens is the secant line, the slope of the secant line that passes through the points P, Q, very closely approximates the slope of the tangent line that passes through point P. And you can let point Q approach P from the right, or you can let point Q approach P from the left, which they do in these bottom 3 figures. Okay. So I think the book does a nice job of you seeing this. And that's why I'm basically using, working with their examples. But are there any questions so far? Any questions so far on what we're doing here? We're trying to find the equation of a tangent line to a curve at a particular point. That's what we're doing. Sydney's good, okay. All right. Are there any questions? Are there any questions about this before we move to the next example? John says, is that the only formula to get the value of the slope? It's how we do it. It is, well, there are different ways to approach the problem, but that is the general approach. All right, let's look at the next example. Thank you. All right, great. In this example, what they're working with is experimental data. So in this next example, example 2, they don't give you a function. They don't give you a formula, but they give you data, and the data is listed in this table here. Okay. So what they're doing is they're estimating the slope of a tangent line from experimental data. And they're saying that the flash unit on a camera operates by storing charge on a capacitor and releasing it suddenly when the flash is let off. So capacitor stores charge, okay, so that when you snap a picture, you have the energy you need. The data in the table describes the charge remaining on the capacitor at time t, okay, in seconds after the flash goes off. Okay, and that's in the table right here. So, all right, what they want to do here is they want to use the data to estimate the slope of a tangent line at the point where t equals 0.04, and I assume we're talking about seconds here, 0.04 seconds. So what happens here? Let's look at the data just briefly. At time equals 0, the charge in the camera is, hold on here, one moment, should be 100 microcoulombs. Okay, yeah, we're measuring charge in microcoulombs. So when you take your physics classes, you're going to learn about these kind of things. But then what happens is the pictures, you're in the process of snapping that picture. So after 0.02, after 0.02 seconds, the charge drops to 81.87 microcoulombs. And then after 0.04 seconds, the charge goes down to 67.03 microcoulombs. Okay, and after like 0.10 seconds here, the charge drops to 36.76 microcoulombs. And what they've done is they plotted these 5 points in the table here. They've plotted 5 points in the table, and they've drawn a curve through the 5 points. Okay. So far, are we okay with the graph? Are there any questions? All right, excellent. And remember, we don't have a formula that for, I mean, the charge, they're treating the charge as a function of time. And clearly the charge drops as time increases because you're in the process of snapping that photo, right? But what happens is you plot the data points, you plot the given data, and you can see you have a curve, but you don't have a formula for the curve. But nevertheless, what they've done here is they've drawn a tangent line, okay, through the point P. Well, they've drawn a tangent line that touches this curve at the point P. And they want the equation of, well, They want the slope of the tangent line, right? They want the slope of the tangent line at the point t equals 0.04. So what they're going to do is the following, okay? What they're going to do is the following. They're going to consider two secant lines, okay? They're going to consider the secant line, well, hold on, let me get that off. Yeah. They want to consider the secant line passing through the points A and P, okay, and they want to find the slope of that secant line, and they also want to find the secant line passing through the points C and P. So two secant lines. Okay. So, and I want to be a little bit careful here. I want to be just a little bit careful. All right. So, if we wanted to find the slope of the secant line passing through the points A, P, okay, what you would do is you would, and maybe I'll put this in, yeah, the secant line, they haven't drawn, Layla says, where's the secant line? They've not actually, well, they've not drawn the secant line passing through AP, those 2 points. But we know we could pass a secant line through those 2 points. The reason they haven't drawn it is because the curve basically looks straight. It almost looks like a straight line. And if they drew the secant line in, you might not even be able to really see it too well. But we know that there is a line that passes through the points AP. And if we wanted to find the slope of the, oh, you're welcome, Layla. If we wanted to find the slope of that secant line, what we would do here, let me just write this here. Okay, this is A. The point 0.04, 67.03 is P. And C, since C is at 0.06, the coordinate 0.06 and 54.88 is C. So what they're going to do is they're going to measure the slope of the secant line passing through the points AP, and then they're going to measure the slope of the secant line passing through the points PC. Okay, that's what they're going to do. And if we wanted to do the slope of the secant line passing through AP, okay, what we'd have to do is, well, it doesn't matter what comes first in terms of y's, but if I were to take 67.03, okay, take the later point, the y value, and subtract the y value from the earlier point, Okay, then what I would do is take the t value. I want to be more careful here. No, actually, I'm taking the later point. I'm taking the later point, the value 67.03, and subtracting the earlier point, 81.87. But then for the t, the difference in t's, I'd have to subtract I'd have to take 0.04 and subtract, thank you, 0.02. And when you do that, what do you get? What do you get when you do that subtraction? If you could compute that on your calculator, I'd appreciate it. And I'll do it on mine too. You should get negative 742. That's right. Good. And negative 742, if you look on the next page, okay, negative 742 is right here. So that's the slope of one of the secant lines. The slope of the other secant line, the second one, going through PC here, the slope of that secant line would be equal to negative 607.50. Okay. So what they're doing is they say to approximate the slope of the tangent line passing through point P, let me take the average of these two values. Let me take negative 742 and add negative 607.50. Let me add those two values and then divide that by 2, which is why they're multiplying by a half. And they get negative 674.75. And that's how they estimate the slope of the tangent line for this second example. Okay, and the reason they chose these two slopes for these two secant lines is the 0.04, the t value of 0.04, which is, we're trying to find the slope of the tangent line where t is 0.04. 0.04 lies halfway between 0.02 and 0.06. So it would make sense to average those two secant lines in order to get the estimate. Okay, intuitively, that would be the way to do it. Okay, does that make sense on this second example? All right, thank you, Lynn. Thank you, Rodrigo, Nicholas, Layla, Lotta, Tanya, and I'm sorry if I don't get all your names, but I do appreciate the feedback. I mean, Anna, Helen, I'm learning your names. Jose and John, Sebastian, a lot of names, a lot of people. Good, good. So, you're going to be doing this too. In your homework for section 2.1, you're going to be doing this process as well. And so, all right, let's go ahead and look at the third example. Okay, the third example deals with a velocity problem. Okay, and what they have here It says if you watch the speedometer of a car as you travel in traffic, you see that the needle doesn't stay still for very long. The velocity of the car is not constant. Okay. But can we compute the velocity at one instant? What's called instantaneous velocity. We can do that. We can do that. So in this example here, and this should be like the example in your book, they say suppose a ball is dropped from observation deck at CN Tower in Toronto. I've seen that tower. I've been in Toronto. It's pretty high, 450 meters above the ground. Find the velocity of the ball after 5 seconds. So they want the instantaneous velocity of the ball right at when t is 5 seconds. You can always find average velocity, right? How many learned how to find average velocity? Maybe in high school or middle school had problems where you had to find the average velocity of something. Sure, Nicholas knows what I'm talking about. And average speed, average velocity, sure. Well, in calculus, we're going to find instantaneous velocity, the velocity at the time t equals 5. Okay? And we note here that if the distance fallen after t seconds is denoted by st, then it can be shown that the distance is equal to 4.9 times t squared. Okay, 4.9 times t squared. How many maybe have seen that formula somewhere? Well, it might be new to some of you, right? Or most of you, because this is Calculus 1. But okay, John's seen it. And it's okay, Sebastian, you haven't seen the formula before. Now you've seen it. And in physics, I want to be careful what I say, but in physics they'll should develop that formula for you. So okay, the difficulty in finding velocity after 5 seconds is that we're dealing with a single instant of time. However, we can approximate the desired quantity by computing the average velocity over a brief time interval. So average velocity, what they do is, now you have a formula. So what they do is they say, well, let's compute the velocity, at 5.1 seconds. Let's compute the average velocity over the interval of time from t equals 5 to t equals 5.1 seconds. Well, that would be change in position. The average velocity is change in position over change in time. And they compute that average velocity as 49.49 seconds. Okay, that's your average velocity. What's that pretty close to, 49.49? I'm sorry, the average velocity is 49.49 meters per second. What's that average velocity pretty close to? Pretty close to 50. So we don't have the instantaneous velocity. That's right, Nicholas, 50. We don't have the instantaneous velocity at t equals 5 seconds, but our intuition might tell us that's pretty close to 50. Well, how can we get a better approximation of the instantaneous velocity? Well, we could go from a time interval of t equals 5 to t equals 5 point what? 5 point, instead of 5.1, which is a tenth of a second, we could find the average velocity that's right from to 5.01. So if we were to find the average velocity from t equals 5 seconds to 5.01 seconds, and Nicholas says we could really go crazy with this. We could really, but yeah, you get the general idea, and that's what they do in this table here. They they compute average velocities over different time intervals, but they're letting the time intervals get shorter and shorter. First time interval is a tenth of a second. The second time interval is 5/10 of a second. The third time interval is 100th of a second. The last time interval where you're going from 5 to 5.001 seconds, that's 100th of a second time interval. And look what's happening here. Look happening. Actually, yeah, it's 49. So I mean, I thought it would be 50, but I spoke too soon. It's actually looking like it's going to be 49, and indeed it is. So your instantaneous velocity is going to be 49 meters per second squared. And you know, basically what they're saying is, if you want to compute the slope of a secant line, you can, what all they did was they let A, here, I want to be a little careful. I don't want to get too technical here. I don't want to get too technical. I think I've given you the the crux of the situation here in this example. But they have a picture here, and basically they're saying the slope of the average velocity will approach the instantaneous velocity as you let the time interval get less and less and less. Okay, and I think that's right. Well, the tangent line, Nicholas, the slope of the tangent line will be the instantaneous velocity at a particular time, at a particular point in time. That's what they're saying. So let me stop the recording here.